Hi, my name is Ismael, and I'm the team lead for Project 23119.
I'm Morgan Halkirk.
I'm Alejandra Hinojosa.
And I'm Kyle Churchman.
And we are all chemical engineering students working on the expansion of the Rainbow Valley Water Reclamation Facility. The project objective is to expand the water reclamation facility's process capacity from 0.75 to 1.25 million gallons per day. The upgraded design must include both a liquid and solids processing train to meet A+ reclaimed water and Class B biosolids standards, while also implementing an odor control strategy. This table provides a summary of the various effluent standards that must be met in order to discharge effluent into the Cantamia Lake located in the Estrella community. However, only a few of these can be accounted for from a design standpoint. The list includes BOD, TSS, total nitrogen, and pH. Our team also decided to upgrade the existing BNR process to include phosphorus removal. That standard usually consists of effluent phosphorus concentrations being below 1 milligram per liter. In terms of biosolids production for land application, the EPA requires the biosolids process design to meet both a pathogen requirement and a vector attraction reduction requirement. The EPA provides an extensive list of process criteria options to fulfill each of these requirements. Our team selected aerobic digestion with a 40-day SRT and a 38% volatile suspended solids destruction rate to guide our process design.
Arizona is one of the driest states, so water conservation is important. 72% of the main water usage goes to agricultural purposes. It is important to use reclaimed water for irrigation. By creating a wastewater reclamation facility, water can be reused within an area to reduce the need for using the Cab Canal or other freshwater resources.
The first step of this water process flow diagram starts with the headworks section. This is where the water flows into the wet well, which was sized for a 30-minute hydraulic retention time and gets pumped through the lift station using 3 new submersible flight pumps with 1 on standby. After the wastewater is pumped, it is then dosed with hydrogen peroxide for odor control purposes. The second step is a primary treatment, which consists of 2 additional conveyor screens that separate about 30% of solids. The third step is secondary treatment. This is where a second train will be added to the already existing one at the plant. Each train will treat about 0.75 million gallons per day, which is half the influent flow rate. Additionally, another clarifier will be added to the process, which can treat about 1.5 million gallons per day, therefore one will be on standby. The fourth step is tertiary treatment, which consists of disc filters, where 2 filters will be added to the already existing ones at the plant. Then the water flows into the chlorination and dechlorination contact basin, which will remain the same due to its capacity to treat 1.5 million gallons per day. From there, the water gets discharged out for use. The newly added solids treatment process starts with waste-activated sludge discharged from the secondary treatment process. This process will consist of membrane module units designed to handle up to 40,000 gallons of sludge per day, thickening the sludge up to 3% TSS while also producing A+ quality permeate that can be sent directly to disinfection. Thickened sludge will then be passed through 2 aerobic digesters in series before being sent to either storage or mechanical thickening via centrifuge before ultimately being sold and shipped off for land application. The digestion process is capable of achieving the required SRT, while wet and dry biosolid storage tanks have 4 and 30-day storage capacities respectively for operation at max capacity.
BioWin software was used to simulate the main primary and secondary treatment aspects of the process. The current facility's tank sizing and influent concentrations of BOD, TSS, and nitrogen were used as a starting point in BioWin for the design. As previously mentioned, our team added a second liquid processing train, which used the same tank sizing as the current process. Addition of phosphorus removal to the BNR process required repurposing 2 tanks currently used for aerobic digestion as anaerobic zones, which allow for the proliferation of phosphorus-accumulating organisms that remove phosphorus from the wastewater. Optimization of the process consisted of incorporating concrete baffling to separate the aeration basin into 4 different zones, adjusting the DO set points of each air zone, and adjusting the Imler, RAS, and WAS flow rates to achieve the desired effluent quality. It is important to note that effluent TSS concentration here seems to be above spec. This is due to the software not being able to simulate filtration. However, The selected filtration units have the ability to remove 85% of the remaining TSS, which is enough to meet effluent TSS requirements.
Project capital costs were broken down into categories for further explanation. Only equipment additions and upgrades accounted for about 45% of the total cost. Contingency was about 20%, which is for the additional costs that were not accounted for. All the labor for the excavation and equipment setup account for about 14% of the total cost. Piping and valve additions and upgrades were about 10% of the cost. The electrical category includes all electrical equipment such as sensor elements and wiring that will need to be installed and will account for about 8% of the total cost. The infrastructure category includes the excavation, labor, tank construction materials, and the building energy costs required to build any reinforced concrete process tanks or infrastructure, and only represents about 3% of the total capital cost. The total project cost will sum up to be about $17.2 million. An increased utility rate by 4% for the first 5 years of operation will result in a 6-year payback period. The net present value is estimated to be about $35.5 million after 20 years, which can be used for the next facility expansion project or can be allocated for other community projects.
Along with construction costs, the expansion project also comes with increased operation and maintenance costs. It's more relevant to look at the O&M costs on a per gallon basis, with a graph reflecting how those costs are impacted over 16 years. The largest drop in costs can be seen in the first year, where O&M costs drop 43% due to the elimination of annual disposal costs for waste, as well as a 24% reduction in energy consumption from upgrading to more energy efficient blowers and pumps. The small spikes in the graph are due to bringing more installed equipment online and the hiring of additional operators as influent production increases. Given the projected population growth for Goodyear, maximum capacity is expected to be reached in year 16. At this point, O&M costs are expected to have reduced nearly 50% from the current costs, while energy use is expected to have been cut by 35% from year 0.
This slide can be used as a comparison between the current and new process layout. The process expansion would be contained within the fence line and process about 1.5 million gallons per day. This expanded process would exceed required flow rate of 1.25 million gallons per day, while still producing effluent that will meet all standards that the current facility operates under. The biosolids treatment process that was added to the facility can create Class B biosolids for land application that recycles nutrients such as nitrogen, phosphorus, and organic matter, while also replacing a large percentage of O&M costs with a new revenue stream for the facility. Odor control was implemented through the injection of hydrogen peroxide to prevent odor from forming in combination with covers to enclose any odors that do form. The capital cost for the expansion would be about $17.2 million.